In this video, we're going to have a look at integration by using a substitution. Now, this works when we've got a function and its derivative in the integral. So let's look at two cases where we would use a substitution. Firstly, this method is useful if you have an integral of this form. Now, we have dealt with this form in other videos. It's looked a little bit different. I've put it a bit more formally, also so it matches the form that's in the information sheet for the exam. What we have here is we have a composite function and we have the derivative of its inner function. So here's my composite function and the derivative of the inner function. Note that this can also be done by using inspection. We actually have been doing it like that up until this point. So if I have the integral of a composite function times by the derivative of its inner function, all I have is f of g of x. So I have that composite function, noting that the derivative symbol is here because remember, to go from an integral to a function, it's actually going from a derivative to a function. So we're actually going the opposite. All right. So I would advise using inspection because it's quicker, we've practiced it, but I will do one of these examples using a substitution. Another case is you almost have an integral structured like that. So you almost have composite and derivative, but there's actually an extra variable. So there'll be this extra x, this extra y that does not fit into the derivative of that inner function. Then a substitution definitely works best because you won't be able to do it just straight by inspection. Right, so let's have a look at this method of integration using a substitution. It might look a bit weird at first, but I'll come back to it as we work through our first and our second example. So often this method is called U substitution because someone decided at some point that we should substitute with a U. By all means, it can be another variable, but we often just use a U. So remember, we were dealing with something in this form here. So when I refer to g of x, I'm referring to the inner function. So we let u be equal to the inner function. So therefore, the derivative of u with respect to x is just the derivative of that inner function. And we can then rewrite du as the derivative times dx. Alright, so notice that what we're trying to do is actually replace anything with an x with a u. Even our dx gets replaced with a du. So this slightly more complicated integral of a composite times the inner function times the derivative of the inner function then becomes integral of fu. So because this here becomes du, so let's actually do that in a color, that becomes du, and because my inner function becomes the u. Right, and actually I should have probably a little thing there because I'm going to go from an integral to the original function. All right. Notice that we have replaced anything to do with the variable x with the variable u. If you find that you have an extra x, it doesn't show you in this generic form, but if you have an extra x in the integral, you rewrite that x also in terms of u. So the idea is to create a far simpler integral. Sometimes it might not look so simple at first, but a bit of simplification makes it easier. If we end up with two variables, an x and a u, then you know you've made a mistake. Right in the last step, you go back and you replace everywhere with u with the expression that had an x in. So your answer still has x's. Okay, you might be thinking, oh my goodness, this is such a complicated method, but hang on a second, it's not. Let's see it play out in an example. So with our first example, I'm going to do it by inspection and by using a substitution. Now first, remember when you're doing an integral question, check does it fit our table? You know, you look at your table and this one doesn't. Does it fit our rule? Can I see that I use inspection in this case? Yes, because remember you can rewrite this function as the integral of 2x times by x squared plus 1 to the negative a half with respect to x. Now the reason why I can use inspection is because I can immediately see this. So let's go back here. I can immediately see a composite function and the derivative of the inner function. Let me show you. So I can immediately see, give myself a bit of space here, I can immediately see a composite function that is this one, and I can immediately see the derivative of the inner function. The reason why this is composite is it's something to the power of negative a half, that's the outer function, and the inner function is x squared plus 1. Now if I differentiate x squared plus 1, I get 2x. So that's the derivative of the inner function. So I've got my composite function and I've got the derivative of the inner function. So all I need to do is to get from there to there. I need to integrate my function f. All I need to do is integrate my function f. That's why it goes from having a derivative symbol to nothing, because integration is the opposite of derivative. Alright, so let's do that by inspection. So I'm dealing with that integral. Let me actually just rewrite it here. Well, actually, I can go straight to the next step. No, let's rewrite it. Integral of 2x times by x squared plus 1 to the negative a half. So I've got to integrate this function here. If I integrate it, I get x squared plus 1. I add 1 to the exponent, remember? So I get a half. And I divide by that again and add my constant of integration. Remember to just pretty it up a little bit, make it look a bit better. Dividing by a half is the same as timesing by 2. We don't like exponents that are fractions, so I'm going to say that's the root of x squared plus 1 plus c. See how quick and easy it is by inspection. So I recommend that that's your first line of call if you can do it. Let's just check, always check that if I differentiate, am I going to get back there? Let's look at this form. The half comes to the front, cancels with the half. Then I minus 1, I get negative a half. Chain rule says I've got to differentiate what's inside. The derivative of x squared is 2x. So I can get back there. Let's now go to that same example and use a substitution, or our U substitution. And we'll look at each step as we go along. Okay. So I'm just going to rewrite the function again. Remember, it's always useful to rewrite it in that nice form where you don't have your fractions, you don't have your roots. X squared plus 1 to the negative half dx. Cool. So my method says, first you let u equal the inner function. So that's what I'm going to do, and I'm actually going to do it on the side here, just in another color. I'm going to let, you don't even need to write the whole let story. We want to make this as short as possible. Let u equal the inner function, which is x squared plus 1. There's my inner function. My next step is then to differentiate u with respect to x. I'm going to do that. I differentiate u with respect to x. So that's the derivative of this whole function, which is 2x. And then rewrite it as du. Now remember, if du over dx is 2x, I can write du is equal to 2x dx. You're almost kind of thinking as timesing both sides by dx. That's kind of what you're doing there. Now there's no spare variables or anything. So what I'm going to do is I'm going to replace everything. Whoops, you get my calendar for a second. Whoopsie. So I'm going to replace where I see 2x dx. Actually, let me rewrite this so you can really see that. So the integral degree, this is just exactly the same thing. I want you to see what I'm rewriting though. 2x dx. Right, so wherever I see u, I'm going to put x squared plus 1. Well, wherever I see x squared plus 1, I'm going to put u. So you notice there's x squared plus 1. So I'm going to replace it with u. Then, can you also see here, I've got a 2x dx. And what am I going to replace that with? Du. So I get an integral that just has u in it. I get the integral of u to the power of negative a half du. And you want to make sure that in this step there are absolutely no x's, which there aren't. Now let's integrate that. That's just using our power rule. So I add 1 to negative a half, which gives me a half. And I divide by half, plus my constant of integration. Pretty it up a little bit. I've got 2 root u plus c. Now in your final step, you don't want any u's because there were no u's in the question. You only want x's. So I'm going to replace u with x squared plus 1. So let's do that. I've got 2 root x squared plus 1 plus c. And have a look, that's exactly what we got when we did it by inspection. Look how short inspection was. Look how much longer U substitution took us. And we know we want to save every second that we can during a test or an exam. So if you can use inspection, rather use it. But let's look at an example now where it really dictates that you need to use a substitution. Right, so in this example, we have this extra x. So let's just try write it out in our usual form where we get rid of roots, we get rid of fractions. So here we have the integral of x times by 2x plus 3 to the power of negative a half with respect to x. Now, obviously, we're searching for that composite function and the derivative. So there's my composite function, but the derivative of 2x plus 3 is 2. It doesn't have an x in it. So we have this extra. We have this almost like an extra x. So it doesn't fit our pattern. So we need to use U substitution. It makes our life a lot easier. So I'm going to rewrite my function over here in that nice form so we can work with it. The integral of x times by 2x plus 3 to the power of negative a half dx. Alright, so at that point, let's go and do our u and our du over dx and see how we go. So let u equal the inner function. So let u equal 2x plus 3. Straight away we go to see what du dx is. Du over dx. Well, the derivative of 2x plus 3 is 2. Therefore, du is equal to 2 dx. Which means I want to see a 2 dx somewhere in my function. Okay, so I want to see a 2 dx. Now, do you see that there is no 2? But that's all right, because 2 is an easy number to introduce as long as we compensate by timesing by half. So let's do that. If I times everything by half, do you agree that I can introduce a 2? There's my 2. That's still equivalent because that 2 cancels out with that half. But now let's handle this x. Let's see what to do with that x. I can rewrite it by rearranging this equation here, u equals 2x plus 3. I can rearrange it to get x as the subject of the formula. So x is equal to, remember my first step is to go u minus 3 and then divide by 2 or times by half. I prefer to see the half because it often makes it easier when you integrate. So all I did was I rearranged that guy to get x. Now I'm able to rewrite everything in here in terms of u. So let's do that. Right, let's go search our 2x plus 3. There's our 2x plus 3. I'm going to replace with u. Then I see that I've got my 2dx, which I'm going to replace with du. And then I've also got my x. There it is, which I'm going to replace with that whole expression there, half u minus 3. So let's do that. So here I've got a half. Integrating, I replace my x with a half u minus 3. Then I replace my 2x plus 3 with a u, and it's to the power of negative a half. And I replace my 2dx with du. Have a look, this is so much easier to integrate because now I can just distribute in and get more than one term. So what I have here is my half and my half give me a quarter, and I'm integrating. I want you to distribute that in. So I get u to the power of a half, because u times u to the negative a half, you add the exponents. 1 minus a half gives me half, minus 3 times u to the negative a half, and I'm integrating with respect to u. I can split this beautifully. It's quarter integral of u to the half. Don't forget your du. Minus quarter, because I'm distributing the quarter, times 3. So actually that becomes 3/4 immediately. To make it easier, 3/4, because you can take the 3 out, integral of u to the negative a half du. Now if I integrate that, just using the power rule, there's my quarter. I add 1 onto a half to get 3 over 2, as long as I divide by 3 over 2. Minus, there's my 3/4. I add 1 onto negative a half, which is a half, as long as I divide by a half, plus my constant of integration. Let's pretty that up a little bit. So a quarter divided by 3 over 2 gives me a 6. U to the power of 3 over 2 is u to the power of 3 rooted. 3/4 divided by half gives me 3 over 2. And that's root u plus c. Then remember, in your very last step, you replace u with whatever the expression was in terms of x. So u is 2x plus 3. So wherever I see the u, I'm going to put 2x plus 3. So I've got 2x plus 3, brackets are important here, to the power of 3 rooted, minus 3 over 2. 2x plus 3 square root plus your constant of integration. So here u substitution was very helpful because it helped you cope with what to do with that extra